Okay, today's lesson is 2.2 polynomial functions, and we are going to spend all of our time talking about graphing polynomial functions. We're actually not going to do any models, so there'll just be one video for this lesson. So, to review real quickly, a polynomial. What is a polynomial? It's this funky little thing right here. This is the way we write it abstractly in math. But the A's, y'all, are just coefficients, and it's just telling you whatever degree that I start with. I'm going to go all the way down to x squared and x, and then no x at all, okay? But what's most important about it is the leading coefficient is the coefficient of the variable with the largest exponent. So that's the leading coefficient. In the past, you've heard it mentioned that your polynomial needs to be written in standard form. And if it's in standard form, then the highest exponent is first. So that's called the leading coefficient of the leading term. It's coefficient of the leading term. So keep that in mind. You're always looking for the highest exponent. That's going to tell us a lot about the polynomial. So what have you had in the past? A polynomial of degree 0. Well, that is a horizontal line, f of x equals 0, or you can think of it in this case, y equals 3. Okay, that's degree 0, horizontal line. Degree of 1 is any linear function. You think of it as y equals mx plus b, but that is a line, degree of 1. Degree of 2 is a quadratic function, and those are parabolas. So that's what you're supposed to be proficient in before you get to pre-cal. Well, now we are going into polynomials, something that's not one of those three. Okay, just again, I mentioned the 0 function is the constant function. It has no degree. But here are some examples. All right, this is an example of a polynomial. Okay, a polynomial, they are defined for all real numbers. Okay, there's no breaks, and they have smooth, rounded turns. So here are some non-examples. Okay, this is an example of a polynomial. This is a non-example. Okay, there are no breaks in your graph, and there are no sharp points or corners in your graph. So when you have to draw them, you need to make sure you do that. Okay, so to continue with when you first learned about graphing, we talked about 2.1 in the monomials. Okay, and we talked about transformations in 1.5. So we're kind of putting this together. All right. So if we have to graph this function 4 minus x cubed, then the first thing I want to do is recognize what the parent function is. And the parent function is y equals x cubed, which looks like that. That's what you have to do in 1.5. Then I go back up to this equation and say, what's different? Well, there is a negative sign in front of my x cubed, which means it's been flipped over the x-axis. So instead of it going up, it's going to actually fall as it goes down. And what basically that point that I have is 0, 0, one of the key points on that graph. And then there's also a 4, and that 4 tells me that my graph has been shifted up. So it's going to look like this, but instead of being at the origin, it's going to go up 4 units. So it looks like that. Again, just a sketch here. Okay, 1b. G of x equals x plus 7 to the 4th. So again, you want to know what that parent function is. And the parent function is y equals x to the 4th. And x to the 4th, both arrows go the same way. They're both going to go up this time. And that point is 0, 0 again. So what is different between my parent function and what I'm told to graph is there's a 7 in it. And the plus 7 means my graph is going to move to the left. So all I would do would be to take that 0, 0 point and move it to the left 7 points on my graph. Flatten it out a little bit. Probably didn't do that good of a job. Okay. Now, the other thing, y'all looked at graphs earlier and you told me what the end behavior was, but you can also do that by looking at the leading term. Okay. And it goes along, with the same thing. Okay. If my leading term, and we're looking at a polynomial like this up here, if my leading term is odd and positive, then my arrows are going to go down and up. You can see that here, down and up. But that's going to help us know how to write the end behavior. Okay, if it's odd negative, they're flipped. All right, and it would be up, down. If it's even positive, even goes the same way. Positive goes up and negative goes down. Again, I'm talking about the left arrow and the right arrow of these graphs. So if you're told to use the leading term test, or we used it, to know what the end behavior of a graph is, because you go look at all this and go, you might be confused. So we're looking for the leading term. In this case, my leading term is the one with the highest exponent. So that is 4x to the fifth. And x to the fifth, the 5 is what I'm looking at to determine that it is odd. And then in front of it, there's not a negative sign, so we know it's positive. And odd positive goes down and then up. And that's what it is. Now, to describe it using limits, okay, what we have done in the past, all right, we have the limit as x approaches negative infinity. X approaching negative infinity is my left arrow of the function, and the limit as x approaches positive infinity. Now, in Delta Math, these are multiple choice problems, so not hard, but you've got to get it down, okay? So the first one is the left arrow, where I have x approaching negative infinity is the left arrow, x approaching positive infinity is the right arrow. Okay, we just said up here it goes down, up. So the left one goes down to negative infinity, and the right one goes up to positive infinity. And that's all you got. Okay, 2b, h of x equals negative 2x to the 6th plus 11x to the 4th plus 2x squared. Again, my leading term happens to be first because it's written in standard form. And this time my exponent is even, but, however you wish to say that, exponent is even, but there's a negative sign in front. So even goes the same way, negative means they're both going to go down. So when I write my limits, there's my left arrow, there's my right arrow, and they're both going to negative infinity. So that's what we have. Okay. Now, something I don't think we've talked about before is turning points. Okay, we have discussed relative max and relative and absolute max and minimums. Those were covered in 1.4. But now we're going to talk more specifically about turning points. It's easy to find these things when you're looking at a graph, but we actually are going to do it from looking at an equation. But to help you remember, I'm going to show you some graphs. So if you look at the zeros, remember the zeros are where we cross. The zeros are where y is 0, and that's where we cross the x-axis. So they're also the x-intercepts. So on each of those in purple, I have that first graph, I have 3 zeros. The second graph, I have 1 0. The next one, I have 2 zeros. And the next one, I have 4. These are all my x-intercepts. Now, my turning points are the peaks and valleys of my graph, and those I have highlighted in orange or put a dot in orange. So on that first graph, I have 2. The second graph, I have none. The third graph, I have 1. And the last graph, I have 3. So what I really want you to point out and what I want you to see is how each of these numbers are related. And I hope you could figure out that every time the number of turning points is always 1 less than the number of zeros. And that is true. So the important thing about that now is that when we look at an equation, it does happen to be a fact. Okay, it's a key concept. Your zeros can be found when you have an equation by looking at the degree of the polynomial. Degree is the highest exponent of any of your terms. Okay. The turning points, as we just saw, is always 1 less than the degree. So it's the degree minus 1. So if I have this polynomial right here, 3x to the 6th minus 10x to the 4th minus 15x squared, then I know it will have at most 6 real zeros, because that's the degree, the highest exponent, and at most 5 turning points. Now, the key is it is at most. If you look at the graph that goes along with this polynomial function here, notice I do not cross the graph 6 times. Okay, it's just saying the most you can have. You can have anywhere up to 6, but you will not ever have more than 6, and you will not ever have more than 5 turning points. So it just really means the most number that you can have. Okay, next we need to talk about the different ways something is named with polynomial functions. I myself am a mother, a daughter, a sister, a teacher, lots of different names for the same person. Okay, we have that in math also. But if we know that a number is an x-intercept, then we also know that it is a zero of the function. Okay, it's a zero of a function. X equals c is a solution of the related equation, and x minus c is a factor of the polynomial. Okay, the whole point of that, y'all, is depending on the context, that's what they're using. But this is the really important one, is understanding that if you are told something is a zero, then you know that x equals that number is a solution, and this is the related factor. So we're going to go forth and do a lot of factoring. So first off, state the number of possible real zeros and turning points. Of course, we're talking about the maximum in each of these cases. Then determine all the real zeros by factoring. Yes, that lovely word, factoring. So 3a says f of x equals x cubed minus 6x squared minus 27x. So the highest power is 3, so the possible real zeros is 3. And my turning points is always 1 less than that number, so my turning points is 2. The maximum number of turning points I will have in the graph is 2. Now, how do I find all the real zeros? Remember, a 0 is the x-intercept, but it is where y is equal to 0. So in each case, I'm going to take the polynomial and set it equal to 0. And now I have to factor it. So when I look at that, the first thing I'm going to do is factor out a GCF, because that's always the first step we should do. And then we're going to find the factors of 27 that subtract to give us 6. And that would be 9 and 3. And I don't know what happened there. So when you have a term of 1, the 9 is negative because the larger number is going to take that sign as well. Okay, so again, if you need help in factoring, y'all, I have some extra practice problems, so please email me or come see me and let me know. All right, so 0 equals, this is the factored form. And remember, you take each factor and set it equal to 0, and then you solve it. So just like I was just talking above, when x is a solution, that's the factor. Well, there's the factor, and there's a solution. There's the factor. Okay, as I said over here, those are the factors, and these are the solutions. Now, what are the real zeros? The real zeros are 0, because you can't forget that first one, 9, and negative 3. So those are the zeros of this polynomial. Okay, so generally when you're asked for zeros, you don't say x equals. If you're asked for a solution, then you would say x equals. Okay, 3b, f of x equals x to the fourth minus 8x squared plus 15. Okay, the degree, the highest exponent is a 4, so that's the possible real zeros that I have. Turning points is 1 less than that number, so it is going to be 3. To find the zeros, I'm going to take that polynomial and set it equal to 0. And then I'm going to factor that polynomial, and it factors to that. I'm looking for the factors of 15 that add to give me 8. And then I'm going to set each factor equal to 0, and I'm going to solve by taking the square root of both sides. So those are my zeros. Plus or minus the square root of 5, and plus or minus the square root of 3. Now, this might have been a little bit tricky or might have a little difficult, and you're kind of going, what the heck just happened? So I'm going to tell you that this particular quadratic here, excuse me, not quadratic, it's actually a quartic, okay? But it is referred to as a quadratic form, okay? Now, it is a quadratic form because anytime you have a polynomial, if you look at this guy right here, okay, it says au squared plus bu plus c. Well, whenever the exponent on this u is a 1, and whenever this exponent of 1 times 2 gives you that exponent, then it is quadratic-like, and we treat it, you can treat it like a quadratic. But what they are doing here is putting a u in, and I'm actually going to show you that and talk about it. It's something called a u substitution. They use the letter u because as you go on later in math, you use it a lot in calculus, so it's kind of just getting ready for that. So I'm going to go back up to this problem here where we did it and show you where it would apply. So when you look at x to the fourth minus 8x squared plus 15, okay, and if I say let u equal x squared, well, if u is equal to x squared, if I square this and square that, then the next step is going to say u squared equals x to the fourth. That's what I get when I square both sides. Well, that means that I can go plug in, instead of having an x squared right here, I can put a u, and instead of having x to the fourth, I can have u squared. So that gives me a quadratic that looks like that. And sometimes that's not as scary to people. So again, I factor by finding the factors of 15 that add to give me 8. All right, u minus 5, u minus 3. I set each one equal to 0. And then when you get to that step, you go, wait a minute, that says u equals 5. My original problem is x. So that kind of should be a clue that u is equal to x squared. So I'm plugging it back in and getting x squared equals 5 and x squared equals 3. So if you feel comfortable, I'm actually going to do that on some future problems so you can follow me as we do that. If you don't feel the need to do this, you don't have to do it. But if you struggle with it at all, if you struggle with the factoring, this sometimes makes it easier for people. Whatever method works for you to assist you in your factoring. Okay? So here are some examples. Another example. State the number of possible real zeros and turning points of each function, then determine all the real zeros by factoring. So g of x equals x to the fourth minus 9x squared plus 18. Possible real zeros, my highest exponent is a 4. One less than that is a 3. So I have at most 3 turning points. To find those zeros, I'm going to plug in 0 for y. So that gives me 0 equals x to the fourth minus 9x squared plus 18. So now I'm going to go over here because 2 times 2 is 4. So this is quadratic-like. And I'm going to let u equal x squared. And u squared then would be equal to x to the fourth. So now it's going to say 0 equals u squared minus 9x plus 18. And I am looking for the factors of 18 that add to give me 9. So that gives me u minus 6 and u minus 3. Set each factor equal to 0. Then I'm going to solve. U equals 6 and u equals 3, but my problems start off as x, not 3's. So what did u equal? Well, I go back up here, and u is equal to x squared. So I'm going to go plug back in x squared equals 6, x squared equals 3. Take the square root of both sides, and I have to remember my plus or minus. So when I get my zeros here, I have plus or minus the square root of 6 and plus or minus the square root of 3. So I hope y'all can see how many zeros is that? 1, 2, 3, 4, because it's positive square root of 6, negative square root of 6, positive square root of 3, and negative square root of 3. So those are my 4 real zeros. Okay, 4b says h of x equals x to the fifth minus 6x cubed minus 16x. Highest exponent again is 5. Turning points is 1 less. That's 4. Find the zeros. I'm going to take the polynomial and set it equal to 0. Okay, this is not quadratic-like, y'all, because 3 times 2 does not equal 5. So it's not going to be like this problem over here. Over here. But the first thing I'm doing is looking, when I have anything higher than a 2 here, I'm going to look and see GCF. It's either going to be GCF or quadratic-like. So I do have a common factor of x in this problem. And when I do, I'm left with x times x to the fourth minus 6x squared minus 16. Well, now I have that quadratic-like. So I'm going to go over here and let u equal x squared. So u squared is x to the fourth. And then I'm going to go back and plug in. Now, I'm only plugging in for x squared and x to the fourth. So my x stays there, and that's okay. I'm looking for the factors of 16 that subtract to give me 6. And that's 8 and 2. Negative 8 and 2 give me negative 6. And then I set each factor equal to 0. Now, x equals 0 is fine, but u equal to 8 and u equal to negative 2 means I've got to go plug something back in because I'm not solving for u, I'm supposed to solve for x. So that's going to be x squared equals 8 and x squared equals negative 2. So x equals plus or minus 2 square roots of 2. Any calculator worth anything will tell you that. And x squared equals a negative number means I'm going to have an I in it. So when I write my zeros here, y'all, I have x equal to 0. Can't forget that guy. Then I have plus or minus 2 square roots of 2. Those are all the real zeros, because if you have an I, it's not a real number. It's an imaginary number. So it's not included in my real zeros, even though I found it when I was factoring. Okay? So we are almost done. Hang on. So next we're going to talk about when we have a zero that occurs more than once. Okay? Oftentimes you can have a factor that occurs more than once. And if it occurs, occurring more than once, if it occurs an even number of times, then we know that it will bounce against the x-axis. And if it happens an odd number of times, it's going to cross the x-axis. So let's go see how that plays in. We're going to talk about that a little bit, or do it. We're going to do it more in a minute. Okay, so same thing we've been doing. State the possible number of possible real zeros and turning points of each function. Then determine all the real zeros by factoring. So I have g of x equals negative 2x cubed minus 4x squared plus 16x. The highest exponent is a 3, which means my turning points is 1 less, or 2. And now I'm going to set it equal to 0 to factor. Okay. Again, they go 3, 2, 1, so there's not any quadratic-like yet. But I do have a GCF, and my GCF this time, y'all, is not only a variable, but also a 2. Now, if you don't see the 2, it's just going to make your factoring more difficult. And the other thing that's really, really important, if you don't want to get marked wrong in Delta Math or IXL or whatever you do, okay, whenever you have your polynomials in standard form and your leading coefficient is negative, when you're factoring, you need to factor out that negative. So I'm going to factor out negative 2x, and that leaves me with x squared minus 2x plus 8, because when you divide these by negative, they're going to switch the signs. Okay, so now I'm looking for the factors of 8 that add to give me 2. And that, of course, is not going to happen. Hold on 1 second, please. Found it. So that was supposed to be a minus x. This is supposed to be plus, which means it's going to change my answer. So hold on 1 more second. Okay, so this is a great example of how you can check yourself. So this is going to be wrong, and I'm going to have to fix it. But so when you factor out a negative, y'all, it changes the sign of each of these. So that should be negative becomes a plus, and plus becomes a negative. So my next step, when you factor, I'm looking for the factors of 8 that subtract to give me 2. Okay, those factors are 4 and 2, but because I had it wrong the step before, okay, so if it's 4 and 2, then I need the 4 to be positive, and I actually need this 2 to be negative. So I'm going to make this negative here. So that one's negative. Okay, so it's x plus 4 and x minus 2. Okay, I'm going to set each factor equal to 0, still having the same issue there. So this one should be negative x minus 2, and this one should be x plus 4. So x is not going to equal 4. It's going to equal negative, and that's a bad negative. X is going to equal negative 4, and x is going to equal positive 2. So when I put those, my zeros, they are, well, I didn't finish. If you divide both sides by negative 2, that will be x equals 0. So my zeros are 0, not 4, but negative 4, and not negative 2, but positive 2. And that's the correct answer. Okay. 5b, 3x to the 5th minus 18x to the 4th plus 27x cubed. Highest exponent again is 5. 1 less than that are my turning points, which is 4. I'm going to put 0 in for y to find the zeros. Okay. Again, common factor, GCF. Try to say it before I do. Great. It is 3x to the 3rd. So when you take that out, I have x squared minus 6x plus 9. And that is a PST, or what we call a perfect square trinomial. This is a square, this is a square, which is very helpful when you get into those conics and other things that we have to do. The square root of 9 is 3, and 3 times 2 is 6. So this factors to x minus 3 quantity squared. Now, set each factor equal to 0. When I solve that, if I divide by 3 and then take the cube root, 0 divided by 3 is 0, and the cube root of 0 is 0. So x is 0 here. All right, when I take the square root of 0, I get 0. So then I have x minus 3 equal to 0, and x equals 3. So my zeros here are 0 and 3. And what's important about it, what we just talked about, is that because of this, well, both of them, they're both repeated zeros. Because that has an exponent of 3, that is a repeated 0. Because this has an exponent of 2, it is a repeated 0 also. So let's go look closely. The last two examples that I have to do, y'all, is putting this graph together. Okay, so the repeated zeros you find, as I just mentioned, by looking at the exponent on the factor. Okay, repeated zeros also referred to as the multiplicity of the factor. Okay, again, that was what I was just talking about with the 0 right up here. This has a multiplicity of 3. This has a multiplicity of 2. Okay, so if it is odd, okay, if your multiplicity is odd, it will cross the x-axis. If your multiplicity is even, it will be tangent or bounce like a quadratic function does. Okay, so let's look at these last two. They want us to apply the leading term test, determine the zeros, and state the multiplicity of any repeated zeros. Find a few additional points and then graph the function. So I'm going to talk to you about how to do this. The factoring goes all along, but when you have to do these problems in Delta Math, you have to be able to plot some points. So that's part of graphing polynomial functions. Okay, so first off, f of x equals negative 2x times the quantity of x minus 4 times the quantity of 3x minus 1 cubed. Okay, so the first thing I have is the leading term. And the leading term you get by multiplying the first terms together. So this negative 2x times 3x, but that 3x is actually cubed. So it looks like that. And if you multiply all that together, the number doesn't matter so much, y'all. You can multiply it out if you want to. 3 cubed is 27 times 2 is 54. But all that really matters is that it's negative and that there's 5 x's. Because there's 1 x right here, there's 1 right there, and there's 3 x's right there. That's why I have 5. So if I have 5 x's, my leading term is odd and it's negative, so that I know my left arrow is going to go up and my right arrow is going to go down when I have to put this together. Okay, now I have to go determine those zeros, so I'm going to plug in 0 for f of x, and it's already factored for me, so they've done the hard work. I just have to go set each factor equal to 0, divide by negative 2, x equals 0, add 4, x equals 4. Take the cube root of both sides, 3x minus 1 equals 0, add 1, and then divide by 3. Okay, so the zeros that I have are 0, 4, and 1/3. Now, 1/3 has a multiplicity of 3, so that means when it crosses the graph, y'all, it's actually going to look kind of cubic. It's going to flatten out a little bit instead of just like a line going straight across. Okay, now the next thing that you're supposed to do, okay, you go plot these along the x-axis, but then you have a table feature. So I'm going to show you how to do that table feature with ClassCalc if you do not have it on your calculator. Okay, so if you have a table feature on your calculator, y'all, you bring it up to me. I'll be happy to show you how to do this. But in case you don't, you all have access to ClassCalc. So I'm going to show you how to do that with ClassCalc very easily, as if you're not graphing. Okay, so you can come here and you can type f of x, just like we have in our problem, and it says negative 2x parentheses x minus 4, close, open, 3x minus 1, close, caret symbol, up to the third. Okay, so that's my f of x. to get the points that I need on my graph. Now our zeros, I don't know if you remember, our zeros were 0, 4, and 1/3. And when you do this in Delta Math, you're going to have to plot some points and whatever the grid is that he gives you for whatever the polynomial is. So I'm going to show you how easy it is to find all the other points on your graph. So if you do f, you got to remember the f of x part. But if I go and do, okay, well, what's f of, let's say he wants me to do -5. Close parentheses. Don't push enter. Okay, just say f of -5. Well, there it is right there. Well, you're not going to be plotting that point. So I'm going to go back and go, okay, f of -4, backspace, -3, backspace, -2, backspace, 1. Okay, well, he might give you a graph. You might have to plot that point. You won't have to plot those others because they'll be too big. But again, I'm just showing you how easy it is to have this on your phone, using this on your phone while you're having to plot a polynomial, or using the table feature on your calculator. And then 0, if you want to put 0 in, that's of course 0. We already knew that. Plug in 1, you can plot that point. Plug in 2, plug in 3, so forth and so on. So you would write that table on your paper, but then you would plot those into Delta Math, okay? So what I did was I went and graphed it for you because I know y'all didn't want to watch me graph it, okay? So here it is, and these are those points that I found, okay? And this is kind of what will happen in Delta Math. He's going to ask you to plot, but when I plotted -2, it was way off my graph. So you wouldn't have to plot that point, okay? So you'll know, and if you need any help with it, just come see me. I do want to point out, I told you that this one was a multiplicity of 3, and so it would flatten out a little bit. I tried to show you more of the graph, but if you were to look more closely at the graph, you would see I kind of zoomed in on it for you. So between 0 and 2, and this is 1, that 0 is 1/3, so you can see that it dips down, and then it comes up and flattens out a little bit before it crosses through. But it's hard to tell when you're zoomed out that much on the problem, okay? All right, last one. H of x equals -x cubed plus 2x squared plus 8x. So first off, leading term. Well, that was easy in this case because my leading term is, of course, -x cubed. And that is odd and negative. So I'm going to have the same up, down. Okay. Now I'm going to set it equal to 0. I have to factor just like we've been doing. So I have a common factor of x, and I got to take out that negative, and let's hope I did the signs correctly. I did. I switched the 2x and I switched to 8. So now, funny, same kind of problem. I'm looking for the factors of 8 that subtract to give me 2. And that, of course, would be 4 and 2. So it factors as such, and I'm going to set each factor equal to 0. Divide by -1. I have x equals 0. Add 4 and subtract 2. So my zeros are 0, 4, and -2. And then I go to my table feature again, which I just showed you. And this is what your graph will look like. And one of the things I want to point out, remember we said that it went up and down. So remember, this is the up arrow, and this is my down. Oh, that was bad, but anyway, down arrow. Back over here, here's my up. It goes up on the left, and it goes down on the right. And that's what we figured out on the first one. Okay, so you're plotting your zeros, and you're plotting those points, and then you know what the arrows do. So now you got your graphs. And that is how you deal with polynomial functions. Hope you all had a great time. Please don't hesitate to email us or come see us if you have any questions. Thank you so much, and y'all have a great day.